Thank you to all the attendees that have already signed in. We welcome you. We're really excited to have you here today. And I am thrilled to be able to have Brendan McGrath share his presentation titled Using Neural Tools, a Practitioner's Guide to Unleashing the Power of Artificial Neural Networks. And Brendan McGrath comes to us from Federal Home Loan Bank of Indianapolis, and he is the Director of Credit Risk Analysis there, and he is essentially responsible for measuring and monitoring enterprise-wide credit risk exposures, as well as overseeing the quantitative engineering group. He has presented for us, and honestly, I've already seen this presentation, and I really thoroughly enjoyed it. So I'm excited to share this with everyone that's joining us, and I don't want to take up too much of Brendan's time because I know he has a lot to cover. So I am going to go ahead and pop this over to Brendan, and I just want to say thank you, and take it away.
So yeah, thanks, Michelle. Just a real quick background. I had presented this at the annual conference in Nashville. So if any of you were there, this is mostly the same presentation, so I apologize. But my intent today, I'm not an academic, I'm a practitioner. And NeuralTools, once you understand how it works, it's really an impressive piece of software, and I have to give a lot of credit to Palisade for putting it together. But unless you know really how to use it and how to manipulate the data to get the most out of it, it's a little bit, it's a lot different than at risk. In at risk, you build your own model. So you select distributions, et cetera, and correlations. In NeuralTools, the neural network actually builds the model for you. So then the question is, well, then what do I do? And the real answer is that you provide the data. And if you've ever worked in machine learning or know people that work in machine learning, there's a disproportionate amount of time collecting data and manipulating data. And actually, the model itself comes after the fact and is actually fairly quick. I mean, at this point, a lot of machine learning algorithms are almost like the commodity, but the real meat of it is the data. So that's the thesis for my main point today, is that if you're going to use NeuralTools, you have to understand how it works, and if you understand how it works, you understand what kind of data to give it. So with that, I'll go to my first slide here. This is a quote from Andrew Ng. He's kind of a leading light in the AI circles from Stanford, but his point is AI is basically the new electricity, and in order to keep your competitive advantage, you almost have to go down this path in some level. And I'll give you a perfect example. There's a guy named Marcos Lopez de Prado who works for a company called Guggenheim, but in one of his books, he sets up a perfect example that, let's say Exxon has a record earning year. Well, before that record earning year happened, before analysts did their write-ups, before et cetera, there were tankers moving. There was satellite imagery of all that. And so if you were able to get that data months before they ever reported earnings, that you had a huge advantage, competitive advantage. I mean, you could predict that they may have had record earnings if you were able to scan those images and realize that there was an increase in tanker traffic and things like that. So that's really where things are going, and in order to maintain a competitive advantage, it's becoming increasingly more dependent on the data and less dependent on the quantitative methods or the modeling methods. Another good example is, let's say, a real common thing for at-risk users is to select a distribution after interviewing people. Well, a good example would be like a Fitbit. So if you ask me how much I walk per day versus actually measuring it on a Fitbit, I mean, you may get a general idea of how much I walk per day, but if you had a Fitbit, you may know exactly, which hour, which days, if I take my kids to dance practice every Monday, that would be reflected because you realize I never walked during those hours. So there's a lot more interesting data and a lot more patterns to be recognized from using Fitbit data. So that's kind of what I wanted to set up. Now, I'm not going to show you how NeuralTools works, because I think that that's sort of after the fact. So this is really, as a practitioner, what sort of things do you need to look out for and what sort of things are important? So, and this is I have 50 some slides, so I'll go through them fairly quickly. So the first question is this the same person? You can see here that as a human being, this is pretty easy to answer. I mean, if you're familiar with Mark Twain, you realize it's Mark Twain on both sides. But from a coding or modeling perspective, it's extremely hard to answer. One of the reasons is you'd have to code everything that's different between the two. So a human knows why, okay, his hair is dark on the left but white on the right. I mean, we know people age. Why is he wearing different clothes? Well, we know that people can wear different clothes. Why is one black and one white? Well, there's different colors. Why is the background different? Why is the shading and lighting different? I mean, if we were to try to hard code rules to recognize this person, it would be extremely difficult. And we may not even get it right. I mean, what makes him Mark Twain or makes it the same person may be very, very complex. It may be the distance between the eyes. It may be the length of his nose relative to his forehead, things like that. So actually explicitly coding this is extremely challenging. But what a neural network can do is if you feed it this information, and the idea with a neural network is you feed it training and testing data sets. So if I feed a neural network thousands of pictures of Mark Twain and thousands of pictures of people who aren't Mark Twain, and I categorize them as either Mark Twain or not Mark Twain, that neural network can learn from those pictures, and it can basically extract what makes that Mark Twain without me explicitly coding that. Now the responsibility I have then is to collect that data set. So for example, I only give it pictures of Mark Twain when he's older. Well, it's going to miss the picture rather on the left, or when he's really young. So that you can see where the data becomes extremely important. But the takeaway here is that the reason you'd use a neural network versus something simpler, because when I first saw NeuralTools, I thought, okay, it's just sort of a glorified regression, but that's not true at all. I mean, it's there to extract very complex relationships, like the example I had where the Fitbit data, I mean, there may be extremely complex relationships that can determine when I walk and when I don't, that may not even be apparent to a human eye, but could be extracted from a neural network. Now, having said that, that doesn't mean that the neural network is the answer to everything. I mean, if something has a very clear linear relationship, a linear regression would probably outperform it. So it's not like the neural network is the answer to all your problems, but it's there to extract extremely complex relationships, and I'll show you some examples of that later. So the first thing is, if you're not familiar with this, and this presentation is really designed as a beginner intro, so if you're familiar with some of these concepts, I may be going over things that are really basic, but I wanted to explain these before you dug into the software itself. So how a biological neuron works, if you look here on the left, basically you get electrical impulses that come in through here. These are called the dendrites, rather. I'm sorry. Here's the nucleus. This is the axon, teledendria, and then you have the axon terminals at the end. But basically what happens is this gets electrical signals from the left. Once those electrical signals fill up large enough, then it will itself send a signal. That's how a biological neuron works. And you see here in the middle we have a step function. So when there's enough electricity coming from all of its connections on the left, so there you can see 4 connections, it will eventually fill up and then fire itself. And when these are all connected, you have a biological neural network. I mean, literally a neural network. And then what they did, and this is actually from the 50s, something called a perceptron. This is what an artificial neuron looks like. And another really interesting thing is, that, like I said, this was developed in the 50s, so you think, well, wow, why didn't we have artificial intelligence, 20, 30 years ago? And the answer is twofold. One, because some of the algorithms, the learning algorithms have been developed fairly recently, and two, the availability of the data sets just never existed in the computing power. So that's why, again, to say that the data is super important, it just comes back to this. The perceptron's been around for a long, long time, and the neural network itself is newer, but really what made the big difference is the learning algorithms and the data sets. So how this works basically is the same. You have input that comes through here, through one of these nodes, P1 and P2. We multiply that by each weight. These connections are weights. There's a bias factor, which I'm going to ignore for right now for illustration purposes, but I basically sum up the node by the weight, and then I put it through some sort of sigmoid function, which in NeuralTools is a hyperbolic tangent function, which is the same thing as a logistic function, except it intercepts at 0, which you can see here. And it's doing the same thing that a biological neuron would do. Basically, when it gets enough information, it will eventually fire forward itself. And I can show you an example of that here. So let's say I input the 2 neurons, I input at 0.5 and 0.75, and then the weights on my connections are 0.6 and 0.4. It's simply 0.5 times 0.6 plus 0.75 times 0.4. I have a 0 bias, that will give me 0.6. The 0.6 is then fed into the hyperbolic tangent function, and then I get a 0.537 output. And that's really it. I mean, that's an artificial neuron. Now, there's a bunch of things you can select for these sigmoid functions, or they can be different functions, but in what Palisade has done is minimized the amount of parameter setting that you'll have to do. And there's basically 2 different types of topology that they offer. One that requires no tuning by the user. The second requires a little bit of tuning. So that's why you have to understand kind of how it works. So now let's say, well, the output I was expecting was a 0.62. I didn't get a 0.62. I got a 0.537. Well, now there's an algorithm called stochastic gradient descent that it uses, and the reason that this is a sigmoid function instead of the step function that you saw before is because you can differentiate it. So it's going to use multivariate calculus then to figure out a min function and then take the error between these two. Okay, so I predicted 0.5, 0.54, and I was trying to get to 0.6. There's an error. I'm going to propagate that error back through this network and readjust these weights until I get the minimum error possible. So now if we go and readjust these two weights, if I adjust them to 10% and 90%, then I get a perfect match. So now I've basically perfectly matched my training set, and I've established the perceptron by itself. Now if you put a bunch of these together, now you have what's called a multi-layer perceptron or multi-layer feed-forward network, which is one of the options that you have in NeuralTools. So you have your input layer, and then you get to choose as the user whether you use one or two hidden layers. You have to use at least one. You get to choose how many nodes you have on each one, and then the output layer would be dependent on what you're trying to predict. So really neural networks are used as a prediction function, either a categorical prediction, so you're trying to predict, high, medium, low, or good, bad, or fail, no fail, or numeric prediction. So you're trying to predict the size of something or the percentage of something. So these output layers would then be my predictions. So let's say I want to say, given some, loan, what state do I think it's from, given the characteristics? And obviously, if I had something like latitude, longitude, this could be hopefully highly accurate. But it could be something that, high balance loans are originated in coastal areas and things like that. So that would be a categorical in terms of which state it's in. Or, like I said, numeric. I'm going to predict the size of something or the length of something. And the thing is that when you put all these perceptrons together, this becomes highly powerful in terms of being able to predict given the data you give it. And then what goes on behind the scenes is all those biases and all the weights are then adjusted through the stochastic gradient descent algorithm. And you don't have to do anything. You just have to provide it a data set. You give it a training data set and a testing data set. So basically you're fitting the data on the training set, and then you're taking it and testing it on the testing data set to see how accurate it is. And we'll cover that later. Now the second function, there's two in the help file. They call them the generalized regression neural net and probabilistic neural net, but really they're both something called what's called a radial basis function network. Also, another couple of things. I have some experience with this outside in terms of neural networks outside of NeuralTools. So I've read through the documentation. There's some things that aren't explicitly stated, so they seem obvious, but I could still be wrong. So by all means, if you have any questions, I would reach out to Palisade. So I'm doing my best to fill in the gaps as a user. But like I said, I didn't develop it, so there may be things I'm not getting exactly right behind the scenes. But basically, the PNN and GRNN, and the only difference between those two are whether you're doing a categorical prediction or a numerical prediction. But they're based on something called a radial basis function. So instead of doing what I showed you before, which is the multi-layer feed-forward network, and the MLF is really the quintessential neural network, which is why I'm going to spend more time covering that than the radial basis function network. But how the radial basis function network works is sort of similar. The only difference is, and I'll show you on the next slide, is saying if I have a bunch of data, so here's two-dimensional data, which is height on the y-axis and weight on the x-axis, and I'm trying to do a category between two professional athletes. Let's say one is a basketball player and the other is, let's say a ballerina or a jockey or something like that, somebody who's going to be light, small versus tall and heavy. The thing is, the nice thing about the radial basis function network is it requires no parameter tuning by the user. It will just learn from the data. And one thing as you're starting out is to use that first, because that will give you a pretty good approximation without you having to hand tune any of the parameters. And what you'll see here is saying, okay, well, the blue category is all one type of athlete and the orange category is another type. So now if I have two new observations, which are the question marks, well, the one seems to be right in the middle of the blue category. So I can predict that would be in category B, whatever that is. Let's say that's a basketball player. Now the downside is it doesn't extrapolate well. So you can see the second question mark down here, it's kind of split between the two, and it kind of struggles. It's like saying, okay, if I try to figure out who's a professional American football fan, and I'm trying to predict if somebody in Moscow is a fan, I mean, they may be close to one of the coasts of the United States, but I can't extrapolate that. That's outside of the data. So one thing about the radial basis function network is you want to give it enough data that covers everything. You never want to extrapolate outside of that because it becomes confused. So just to give you an example, and I deal with financial data, but I'm going to use images to kind of make my point, because what I'm trying to show is there could be very complex relationships in the data that you have, and the only way to extract them is through something like a neural network. In the examples I have, it's really apparent what they are because they're handwriting or facial recognition. But in reality, the data I work with doesn't look like anything. It's financial data. So my first example is something called the MNIST database, which is a really common database for machine learning. It's a series of handwriting samples from 0 to 9. There's 70,000 total samples, 60,000 for the training set, 10,000 for the testing set. Each sample has one categorical output. So it's not a numeric output, it's 1 through 9. And another thing to be aware of also when you're dealing with machine learning, categorical information, never make that numeric. For example, let's say I have state data, United States, I would never want to make like Indiana 1 and Illinois 2, et cetera, et cetera. I would want to make those completely separate. And actually, you can read the documentation for NeuralTools, but NeuralTools behind the scenes will turn categorical data into numeric data the correct way, which is called one-hot encoding, which basically says if I have 50 states in a single column, it's going to turn that column into 50 columns, and then it's going to put a 1 wherever the relevant state is. And that way it's saying, 1 and 2 aren't close at all. I'd never want to say, okay, California is a 1, and, another state is a 2. That's alphabetically close, but it's not geographically close, because you're going to confuse the algorithm. So here the output is 0 through 9, but it's a categorical, not numeric. And each pixel has a value from 0 to 255, which is grayscale. So I'll give you an example of this. And here's some handwriting examples from the database. And what I'm trying to show you here is there's a wide variety of what we would call, 5s and 2s and things like that. We can see that these are both 5s, and because we're humans, we recognize these both as 5s, these both as 6s. But they're different, and our data may be the same way. Like, for example, the data I deal with, does every failed bank, okay, let's say I'm doing credit analysis on potential failures of banks, do they all look exactly the same? The answer is no. There's some commonality. Same way in the handwriting sample. Do all the 5s look exactly the same? Do all the 6s look exactly the same? No, there's same thing with the Mark Twain example. They're all Mark Twain, but they all present themselves in slightly different ways. And if I had to try to hard code what makes a 5 and a 6, it would be very difficult. For example, here's a sample of nothing but 8s. These are vastly different. You can see sometimes the scan isn't complete, sometimes there's a gap on top, sometimes people write from top to bottom or bottom to top, but yet these are all 8s. And just to give you an example, I can actually show you the Excel file that I used to create this. This is all doable within Excel. Let's see if I can recalculate this. Can you see that, Michelle, the Excel file?
Sure can. Yeah.
So you can see some of these are pretty clear, some of them pretty rough. I mean, that looks like an H to me. I mean, that doesn't look too much like a 4. That could easily be confused for a 1. Those 5s and 7s are pretty close. But as you can see as I go through this, I mean, it would be a challenge for me to try to say all 3s look exactly like this, and I would expect all the pixels to always be in these areas. It just doesn't work that way. So let's go back to the presentation here. So the question is, well, okay, how do I deal with this? Well, this data actually surprisingly looks a lot like my financial data. So behind that 8 is a series of numbers. It's really a matrix of 28 pixels by 28 pixels, which would be 784 total pixels. So what I need to do in order for the machine learning algorithm to learn what's an 8, what's not, is to take that matrix and turn it into just one vector. So I've gone from an image to a matrix of data, and then I take that 28 by 28 and basically stretch it out into a single row, 784 pixels long. And now at this point, the data looks exactly like the data I deal with. We've got rows and columns. And then what you'll do, and you can show, and Palisade or Michelle will show you this when they show you how to use NeuralTools itself. But basically, from each one of those rows, I'll give it a category to train it on. So I say, of this string of 784 pieces of data, this is a, quote, 8 or a 9 or a 1. And then what I do is then feed that through a neural network. So you can see here on the left, that 8 is really 784 input nodes. So I've got nodes 1 through 784 that gets fed through the neural network. Now from there, I can choose whether to use 1 or 2 layers. Basically, the more layers, the more nodes you have, the better it can fit complex data. However, there's also a risk of overfitting data, which we'll talk about a little bit later. Generally, the MLF is used more often by practitioners, but it requires more input from the user. You're going to have to run it multiple times and tweak parameters or hyperparameters and change the topology till you get what you want. So usually what I do is just put it through the radio basis function network first and see what I get and use that as kind of my target for the MLF. But then from here it goes through and then it'll output some sort of category. And what I'm hoping is once I put in all 784 pieces of information, the highest probability from 0 through 9 will pop out an 8. So the node that's associated with 8 will hopefully have the highest output number. Then it will then assign that to a categorical, say that, okay, from when you're giving me an output choice from 0 through 9, this is a, quote, 8. And if it's not an 8, then the learning algorithm, the stochastic gradient descent, will then go and rearrange all of these weights until it does work. And if you think about it, there's a massive amount of weights. I mean, let's say I have 100 nodes in the first layer. That would be 784 by 100 different connections, potential connections. So you can see there's a lot going on. And dimensionality reduction, which I'll talk about a little bit later too, is hugely important in machine learning because overfeeding it data that's irrelevant can cause a lot of problems. One, you could have a bad model, but two, it just could take forever to converge to an answer. So given that, you can see that, okay, this is a huge amount of data that I'm providing. I've got 60,000 observations in terms of the rows. I've got 784 columns. And as one point here also, just a general point of rule of thumb rather, you want to have a lot of observations and you want to minimize the number of dimensions or categories you have. So for example, if I could compress those 784 pixels down to something less, it may be better for the algorithm to run. I'll give you a good example. Let's say I'm trying to predict mortgage defaults. And I have a data set of FICO and debt to income, but I also have shoe size and things that just aren't relevant. That's just going to confuse the algorithm. It's a dimensionality problem in that DTI or debt to income and FICO scores and other things are highly relevant and other things aren't. So you don't want to pass it any more information than you have to. And that's a whole nother discussion, and I'll touch on it briefly here. But the point is you want your data to be tall and skinny because it will learn well from that. As skinny as it can be. You don't want to compress it where you're losing valuable information. What you don't want is something that is basically short and wide. And I'll show you an example of that here in a second. So just to summarize the MNIST, okay, so I put that through NeuralTools. I'm not going to show you what I did, but we're trying to see, okay, the PNN, how well did that do? I ran this to the PNN because it ran quickly. So I achieved 92.3% accuracy using NeuralTools, which isn't bad at all. And in fact, this is a first pass. Now, can that be better? Probably. I mean, I just did this really quick. And that's the thing about running a neural network. It can generally always be improved through tweaking of parameters or changing the data set. But this is kind of a quick and dirty, let's see how well I could get this to be. And 92% accuracy isn't bad, especially when you're going from nothing to 92%. It's not a bad result at all. Now, having said that, I would be real careful about accuracy numbers because if you have a really rare occurrence, so let's say I'm trying to predict some sort of rare disease, which is equivalent of finding a needle in a haystack, just predicting a lot of hay will give you a high accuracy ratio, which doesn't really do much. So you have to be aware of certain things to look at in terms of accuracy. Now, for the handwriting, it's perfectly fine because each one's equally likely. But if you have very, very rare occurrences of something, you're trying to predict those, be aware of that the accuracy is showing you not only the successful predictions, but also the fact that it's not something. Which, if it's really rare, the fact that it's not something can occur very commonly and give you a high accuracy ratio. But let's just look at the results real quick and see if they make sense. So we'll look on the left and say, okay, for a 0, I had less than 1% in terms of bad prediction, and that makes a lot of sense. Now let's go down our bad prediction and say, okay, where did this seem to struggle? Well, right here I'm saying, okay, an 8. It really struggled with an 8. In fact, it miscategorized 17.5% of the 8s, and you say, well, gee, why did that happen? Well, let's go across the confusion matrix and see. Well, I showed you an example of 8. They get real sloppy. An 8 and a 3 sometimes looks really, really similar. An 8 and a 2 or even an 8 and a 1 could look similar, 8 and a 5. And you can see things that have really, really low error rates, like a 1. How do you confuse a 1? Well, you may confuse it with, it looks like a 3, but a 1 is really confused with anything else. Now, if you look, a 7 was confused with a 1 fairly frequently, which makes sense. So this gives you some idea, okay, well, where am I running into trouble? And here I'd say I'm running into trouble with 8s. The most, but that's just a function of the data set. So, and this is output from NeuralTools if you haven't used NeuralTools before. So now let's talk about dimensionality for a second. So there's something called the curse of dimensionality. If you've dealt with optimization functions before, you're well aware of this, but I think it's worth reviewing for the purpose of this example. So the curse of dimensionality basically says the more dimensions your data has, the amount of data you need to arrive at a decent result grows exponentially. So for example, if I'm trying to predict, let's say, the rate of a disease, if I give it a bunch of data that just doesn't matter, okay, I don't know, I'm trying to think of something, but just massive amounts of data, like my favorite shoe brand or something like that, it's just going to make the data super sparse. I mean, if you think about this, if you slice something fine enough, there's not going to be many people in that category. And then the algorithm struggles because it's trying to find a commonality. So for example, the one that I gave before for the professional athlete in terms of height and weight, you can see that there's 2 pretty clear clusters. But if I give that more information, people might be close in terms of height and weight, but they may be very far in terms of the other data that I give it. So now what you want to do is look at your data in terms of how can I reduce dimensionality and what impact does that have? So I'll give you an example. Let's say you're trying to find the optimal cookie. So here's an optimization problem. So here are my choices for cookies. I've got 10 shapes I can pick from, 10 colors, 10 flavors, and 10 brands. So the first thing I go through is, okay, let's say I have 0 dimensions, which means I'll take any cookie. So I have one choice. and the optimal choice is whatever I get. So you can see that's 10 to the 0 power, one choice up here. Now let's say, okay, but I'm trying to get the best shape. Well, now the optimal choice is somewhere 1 of 10. So now I have 10 choices of which cookie to pick. So I've gone from 1 to 10. Now let's say we introduce color. Okay, well now I have two-dimensional data set. So now I've gone from 1 to 10, now 100 choices. Now if I'm trying to mix and match shape and color, this algorithm is going to try to find the optimal cookie at 1 out of 100 choices. Now when we add flavor, you can see where this is going. It becomes a cube. And now we have 1,000 potential choices to pick. Now let's say I just don't care about the shape. It just doesn't matter. Well then, and for my purpose, it doesn't matter. So why would I pass that in? It's making the data extra sparse. A good example too is the MNIST, the handwriting database. Let's say that handwriting scan was in color. I'm just trying to find image recognition. Does it really make sense to pass 3 times the amount of data in RGB field than it does in grayscale? The answer is probably not. Now if I wanted to predict, given the color of the ink, I'm trying to predict something else, then it would matter. But if all I'm trying to do is handwriting recognition, the color won't matter. So compress that down to grayscale. And also the 0 through 255 doesn't matter. The example that I gave, I actually compressed that down to quintiles. So instead of having a 0 through 255, I turned it into 1 of 5 potential shades, because what I found is it just doesn't matter. So now let's add the final dimension. So now we've got 10,000 choices. So now we've got, out of shape, flavor, color, and brand, I have 1 out of potential 10,000 choices for my optimization function to pick sort of the best cookie. And this is actually a real representation of a 4-dimensional or hypercube. And one neat thing to show, this is just an aside which I showed at the annual conference, but I'll show here too, is if you think about this, a one-dimensional object is bordered by 2 zero-dimensional objects. So a line segment is bordered by 2 points. Okay, a square is bordered by 4, so a 2-dimensional object is bordered by 4 one-dimensional objects. Okay, then we have a 3-dimensional object, which is a cube, is bordered by 6 2-dimensional objects, which are squares. So then the question is, does that relationship hold for a hypercube, which is a 4-dimensional cube? And the answer is yes, it does actually. There's 8 hidden cubes in there if you're interested. And thanks to Neil deGrasse Tyson, I saw that on one of his presentations. But that just gives you an idea of the sparsity of the data and the amount of data that now we have to comb through to figure out our optimization function. So now just what are some rule of thumbs for reducing dimensionality? Well, a couple easy things is one, first of all, just look at the data. I mean, the first thing anybody does in terms of machine learning is open up the data set and see what they have. Remove, like I said, unnecessary variables. For, mortgage prediction model, if I had shoe size or something, I mean, I would just remove it. It doesn't matter. Remove variables that just don't move that much. That's a potential solution. Remove highly correlated variables if you can eyeball those. Reduce categories. So, for example, and I'll walk through these in a little bit more detail, but let's say I have a mortgage portfolio and 90% of those loans are in 4 states. Does it make sense for me to pass all 50 states into my machine learning algorithm? And the answer is maybe it does, maybe it doesn't. Maybe it makes sense to pass the top 5 and then put the remainder in its own category. And this is a whole separate topic. There's something called, the dimensions are also something called features. So let's say height and weight, there are 2 features of the data set. So feature selection and what's called feature engineering there's a lot of research that goes into that. I'm showing you ways of just to eyeball it, but there's actually more technical approaches to that. Some principal component analysis, for one, is very common. And actually principal component analysis is an option in stat tools. So if you're interested in that, that's probably a whole nother topic. But in terms of correlated variables, I mean, there's ways to actually determine that. But let's say I had height and weight and BMI as my variables. Well, BMI is a function of both height and weight. So I don't know if I need all 3 of those variables. I mean, I may need height and weight separately, depending on what I'm trying to predict, or BMI or body mass index might be enough on its own. I'll show you one other thing real quick. I'll go back to one of my original slides. But when we're talking about dimensionality reduction, I'll show you essentially what we're talking about in terms of principal component analysis also. So if I go back to the categorical. Okay. So here, if you look at this data set, you can see, well, if I put a line set, so we're using the radial basis function to determine the clusters, but you can also use, a linear classifier, which I could put a line right between these 2 in 2-dimensional space, and anything on this side would be category B, and anything on this side would be category A. However, what something like principal component analysis does will compress this down to lower dimensional space. So for example, this is 2-dimensional data. But if you look, I can actually separate this data by weight. There's a line between this. So imagine if there's a light up here that basically projects this down onto the x-axis. So I'm going from two-dimensional space to one-dimensional space. I could still separate this pretty well simply by separating it by weight. Now I can't do that by height because you see there's overlap, but I can actually reduce it down to one dimension. So I'm going from two-dimensional data to one-dimensional data by simply reducing it down to its principal component, which would be weight in this example. But that's a whole other conversation, a whole other topic, but it's something worth looking at if you're interested in a more technical way of reducing the dimensionality of your data set. But having said that, if there's variables that never change, obviously if my whole data set comes from one state, just remove that state. That's not going to make a difference. I'll also show you another example of a data set that I have that illustrates this point and one other point about dimensionality here. So let me get back to where we were. Here we go. Right here. So again, view and analyze the data, remove unnecessary variables, any low variance or low sensitivity variables, remove those, highly correlated variables, and bucket categories if you think it's necessary. Now, one thing about compression, and this is the same thing in terms of like MP3 compression, sometimes you can lose valuable information. So it's really up to the user to understand what's the signal and what's the noise. It's not like you always have to do this. There might be valuable information that you didn't even know was in there. I may think shoe size doesn't matter, but maybe it matters for some really weird esoteric reason I didn't know. So generally what you do is try to run everything you can first and see how it performs, and then iteratively reduce dimensionality and then run the data and then try to get it the highest accuracy ratio you can or the lowest error. Another couple things too. You need a way to impute or drop missing data. So obviously there's ways in NeuralTools itself to impute data, but there may be a way before you even pass it to NeuralTools. You either drop missing data or impute it. There's multiple ways to do it. You can actually use at-risk to do basically a Monte Carlo imputation if you want to. And then outliers too. It's going to try to fit outliers because again, the machine learning algorithm is going to try to find highly complex relationships, and it may fit outliers that just don't matter. So another thing you have to do in your data set is to adjust or remove outliers when necessary. So back to the cookie example. So now let's say, okay, I only care about 3 shapes. I mean, this is just a back of the envelope kind of dimensionality reduction, but okay, I only care about circles, squares, the other ones I don't care. I don't care about the color at all. I just care about the flavor, and the flavor I care about is chocolate. Anything that's not chocolate, I put in the same bucket. Let's say there's only 2 brands I really care about also, and I'll bucket the other one. So now I've basically just off the cuff reduced it from 10,000 choices to 18 by simply doing that. And again, it's up to the user to do this, depend on what you're trying to accomplish. So again, NeuralTools will do whatever it needs to do given the data that you've given it. It's up to the user to provide the data that's relevant. It's kind of like saying garbage in, garbage out, but it's not quite true because you may have highly accurate data. It's not garbage data, but it's irrelevant to what you're trying to predict. And like I said, it's up to the user to try to figure out what to do with that data because NeuralTools is going to try to fit it no matter what you do. I'll give you an example. I have a data set over here which illustrates kind of a really neat example. This is a data set from AT&T called AT&T Cambridge Facial Recognition Data Set. And if you notice, this is a 64 by 64 pixel image. On the left is the actual image here, and on the right is basically an average of all the images. There's 40 subjects. Each one has 10 photos. So if you go through, you can see the actual photo on the left and the average on the right. Now, if you look at some of these photos, it kind of gives you some idea of what that like a facial recognition algorithm would pick up. I'll give you a good example. So let's say this one. I mean, what seems to be really, really apparent on the right-hand side? And the answer is, well, his eyes and his brow. And the mouth and the nose seem to be a little bit fuzzy. So whatever is making this person, individual 28, you can kind of tell from the average matrix that it's his eyes or his brow. And in other ones, people sometimes wear glasses. Here's a good example. You can see on the left picture, he's not wearing glasses. On the right picture, he is wearing glasses. Now the question is, can NeuralTools do this data set? And the answer is no, not without adjusting it. And the reason for that is a couple things. Any limitations in NeuralTools comes from Excel, generally speaking. So NeuralTools does everything it needs to do, but you're limited in terms of what you can pass to Excel. So are you able to pass, high resolution video through Excel? I mean, obviously not. Now, these aren't high resolution images by any means, but you have a massive dimensionality problem here, and that is that the image is 64 by 64 pixels, which is 4,000 pixels. However, I only have 40 subjects with 10 pictures each. So it's a really, really wide data set. So I only have 400 observations, but I have 4,000 dimensions or 4,000 features that I've got to comb through. And when you try to put that NeuralTools, it'll say, you know, the data set's too wide. It's trying to like predict something with only 1 or 2 observations. It's just not enough. Now, I'll show you the example for the MNIST database. There's ways to reduce that just off the cuff. I mean, there's a lot of white space in those on the handwriting recognition. You can cut out the borders, you can remove the white space, but here it's like, it's not quite as apparent. I mean, it seems like every pixel kind of counts. It's already not really high resolution. There's not a lot of border space, etc. You can actually use principal component analysis to reduce this down, which isn't really the subject of the presentation, but my point is this data set's not going to work. It's way too much information and not enough observations. And in fact, if you try to put this into NeuralTools, the raw data set unadjusted will say wrong. It's too wide. I'm not going to be able to deal with this. And this is a really big problem, not just in NeuralTools, in any sort of machine learning data set. If you come across data like this, you'll need some way to reduce this down to something that's going to work, which would be probably, 400 features or less. And principal component analysis, that's a whole nother conversation and maybe a topic for another webinar or presentation. But I wanted to show you this data set just to give you an idea of what works and what doesn't. Now for me, I need financial data set. It's really rare that I would have a couple observations and like thousands and thousands of features. But it's possible in really sparse data that you can run into that problem. So let's go back to the presentation. So here's just a kind of off the cuff, back to the envelope dimensionality reduction. But again, there's a little bit more sophisticated ways if you're interested. Now I'll show you another thing that you can do with a neural network is function approximation. And I'll try to go through this quickly. So this is Goldstein Price function, which is a common optimization function. And if you notice, it's a very, very hairy function. I mean, this is really, really ugly. I mean, you could use a potentially Taylor series to do this, but there's a lot going on here. And the question is, well, can I put this, let's say this is data that I have, let's not say I have the mathematical function, but I just have observations from this. Can the neural network, quote, learn the function? And the answer is yes, it can, to a point. So here I have an example. So let's say you can see here are the training and testing set I'm giving it. So I'm only giving it 10 observations. I'm running it through the radial basis function network because that runs much quicker than the multi-layer feed forward and gives me much better output. And then I'm using a grid to predict the function itself. So with only 10 observations, it didn't do a great job predicting what the function actually looks like. It's just kind of a flat plane. But now when I increased observations to 50, now it's kind of getting there. You can see here now my training and testing set is less sparse and it's doing a better job predicting. Now if I give it 100, you can see it's starting to form and look like the actual function itself. With 500 samples, it's even better. And you can see too, I mean, at some point, you can start to give it too much data. You've already kind of reached mostly what you need to accomplish. We'll give it then 1,000 samples, and it's getting better and better each time. You can see the data is much more dense, I guess, and the neural network is doing a much better job. And this is all done in NeuralTools. I mean, this is all done in Excel. You can see that this is an Excel graph. And then we have one more version of this. Which would be, let's see, for some reason it's not, there we go. So now I have 5,000, which, is essentially so dense, it's basically the same thing as the prediction variable. So now I've done a really, really good job of approximating that function. And I don't need a mathematician to have me do this. I just need the data. Now, is it perfect? No, it's not. I mean, it's a little rough, but it's probably very, very close for any sort of practitioner's needs. Now, one thing I did, and maybe some of you on the call have already picked up on this, I've sort of cheated you in one way with this example. And the question I have, too, is how did I cheat you? And one thing to think about is, well, what's wrong with the data that I used to train the network with? And the answer is nothing's wrong with the data. It comes from a function. It's perfect data. In real life, we never get perfect data. It's noisy data. So we're going to talk about then what's called overfitting the data. So now let's say I have, let's see here, let's go to another example. So let's say this is now my training set and I provide this to the neural network. It's pretty sparse data, but if I provided that to the neural network, it would perfectly match this. I mean, it would not struggle with this data at all. You can see there's some sort of function, and this I've represented this in terms of a function, but the neural network would do the same thing. I would have 0 errors on the training set. So if I provided this and I said, okay, here's the input, here's the output, I would get 100% accuracy ratio, 0% error. But the point of a neural network then is to generalize to do predictions right? I'm feeding it training and testing set for a reason. I'm trying to make numeric or categorical predictions about future data I have. So now let's say the future data looks like this. Well, we've got major problems because there's huge errors between what I predicted and what I actually observed because I overfit the training set. I mean, another way to think of overfitting is, let's say, somebody gets a custom suit. That perfectly fits that individual, but does it generalize to the population well? And the answer was, almost certainly not. Now, the goal for a neural network isn't to find a custom-made suit, but to find general, medium, large, extra large sizes that generalize to the population the best possible. So for this example, now let's say that I get small errors. Let's go back to the training set. I get small errors using a linear approximation. So it doesn't fit the training set as well as the polynomial I had before. However, it fits the testing set much, much better. And it's a much, much better generalization of the data. And the data you can see here is noisy. Unlike the function approximation that I showed earlier, it's a much, much better setup predictive model. And this is just a couple examples. So let's say, okay, I've got a 1% error in my training set. Hey, that's great, but if you get a 30% error on your testing set, that's not good. And if you're not familiar with training and testing, just to go back to it, when I have a big data set, I carve it into two pieces. One piece is used to train the model, but once I train that model, I test it on the testing set, which is an out-of-sample set, to see if it fits that well. Because again, what I'm trying to do is generalize and predict. And if I overfit the testing set, it's not going to generalize well. So basically think of it as the custom-made suit or like a spandex suit that fits one person really, really well. But now when I try to fit the general population, it's not going to work at all. So for the first example, yeah, I fit the training set really, really well. And you have to be really careful about this because a multi-layer feed-forward network, because there's so many, with 100 nodes and 2 hidden layers. So two or more hidden layers is what's defined as a deep neural network. That can fit highly complex data, and it can fit, almost anything. I'd say anything, but fits most data very, very well, which is a huge problem in terms of overfitting your data. So sometimes you have to scale that back, and that's part of the reason multi-layer feed-forward network doesn't work as well out of the gate, because you really need to kind of tune those parameters. You need to scale back the layers or scale back the nodes. And what some people do is just max it out and say, okay, I'm going to get 100 layer 2 nodes, but you're going to have high probability of overfitting your training set. So on the user's end, you have to kind of tweak some of those parameters. The radial basis function network will just fit it pretty well right out of the gate. So the first example, I have a 1% training error, 30% testing error. That's not. I've overfit my training set. Now the second example, I get the same 30% error on both. I mean, it just didn't do well at all, so it underfit. So in that example, okay, my model's too simple. I maybe didn't pick enough nodes, or maybe I need to increase the layers, but I put a much too simple model on a data set that's much more complex. So I would get an underfitting or high errors on both. Now in the third example, I get a good fit. I get a 5% training error, which is worse than the first example, but it generalized the testing set much better. There's no hard and fast rules for these things, and obviously they're dependent on your data set and how noisy it is, but this is an example to show you what you're going for. When you use neural tools, you're trying to get the training and testing set as close as possible, and you want that error on both to be fairly low. So just to give you an example, here are some things that I ran, and this is really, really noisy data, by the way. So I just got all the bank failures going back from 1997 to before I gave this presentation in Nashville last year, which is 584 bank failures. I had about almost 4,000 randomly paired healthy banks with failed banks. So I have equal size data sets. So I sort of eliminated that problem of accuracy ratio when I have a small amount of failed banks but a large amount of healthy banks. So it's about 50-50. I did about an 80-20 training testing mix. I deleted anything that didn't have the full data set. I could have imputed it, but for the purposes of the example, I just deleted it if it didn't have the full data set. And then each sample contained 39 financial ratios, which I just dumped in there. This is really, really rough data. And it's a binary classification, so it's basically active or inactive. A couple of things too. Binary classification, it's not in the presentation, but if you're trying to classify something as 0, 1, or good, bad, etc., and you can Google this on your own, but there's something called the recall and precision ratio, and also called a F1 statistic. I'd highly recommend using those. You can calculate those on your own if your data is very, very sparse, if you're predicting something that's very rare. So for example, like I said before, the needle in the haystack, if you're trying to predict whether or not I'm in New York or not next week, I mean, you can just guess not on most cities and you'll be right. Let's say last week you don't know where I was, but the probability of me being anywhere in the world is equal to New York. You get a high accuracy ratio by just saying not New York. So it's kind of like the problem of saying, yeah, it's mostly hay and I don't care where the needle is. So if you are doing binary classification and you're trying to predict something that's really, really rare, then I would Google precision and recall in F1 because that can supplement your accuracy ratio. And it's easy to calculate from the confusion matrix that precision sheet generates. So then for this example, the multi-layer feed-forward networks seem to generate the lowest error rate. And like I said before, the data is noisy. And if you look at this, I've sort of violated my own rules. I've got just dumped nothing but financial ratios and data in there. Now, there's several profitability ratios. Are they highly correlated? Yeah, probably. There's several leverage ratios. Are those correlated? Yes. Do I need all of them? Probably not. But I just dumped what I could in here, and there's much more. And you can see from this too, the onus is on me to get this data set where it needs to be. If I have a problem fitting this data set, there's probably one of two issues. Either I messed up the data set, or it's just not possible to extract what I'm trying to extract from it. So it's probably not likely that NeuralTools was the problem. It's probably the data set or me that's the problem. But having said that, there's something called CAMELS ratio, which is capital adequacy, asset quality, management, which we usually don't put in quantitative models like this, earnings, liquidity ratio. So these are all basically CAMELS ratios without the M in there. And they all overlap, so there's probably high correlation, but yet I just still dumped it in the model. So then the question is, how accurate was this model 4 quarters prior to failure? So I got about, for the training case, okay, you can see, for the training case, I got 90+% accuracy. However, if you look at the testing case, I got less than 80% accuracy, which is good but not great. So it's overfitting my data set 4 quarters prior to failure. Now, having been a practitioner, is the problem the model or is the problem the data? And the answer is the data, because some banks show signs of failure 4 quarters prior, but many of them don't show that early. And the example that I would give is, what's the chance that I fall off of a mountain cliff if I'm here in Indianapolis, Indiana? Well, there's no mountains around, okay? So if you're trying to predict that right now, it's a very low probability. Now, let's say I'm in the Alps next week. Well, that probability went way, way up. Now, you can say, well, your prediction was off, but if you didn't know where I was going to be next month, then that's completely reasonable to say that it had a low probability of me falling off a cliff. Same way with, okay, what's the probability of a bank failing? Now, having said that, there's banks that show signs very, very early, but generally speaking, the data set 4 quarters prior is a little noisy. So now when I change the data set, okay, let's say 2 quarters prior, so we're a little closer to the actual failure. Now we get different results. Now the training case, I've got, let's say, 95% accuracy ratio. In the testing case, I've got above a 90% accuracy ratio. So that looks pretty good. And not only that, but it looks pretty good having given the extremely noisy and then probably too large of a data set. I mean, I'm passing more dimensions or more features to that data set than I really need to pass. So now the process would be, okay, well, I've kind of got a baseline here. Now I'll go back to my data set and see what I can do. I can go back and I can add the missing pieces and impute missing data. I can, eyeball some of the ratios and remove things that I think may not be predictive. And that could actually make my model worse. And that tells me, okay, I've taken out something that's important. And actually, I've had that happen before where I say, okay, I've got 2 leverage ratios here. I don't need both. And I take them out, and it makes the model worse. And part of the reason that is because one may be telling me something important in the case of a failure that the other isn't. Even though they're highly correlated, there may be something really, really important in the case of the failures in one of the 2 ratios. So there's a lot of onus on the practitioner to go through the data set and put that together to get good performance out of the model. But having said that, NeuralTools is a really impressive accomplishment. I mean, you're getting really, really, really powerful machine learning algorithms in Excel. And if you use the radial basis function network, it's very user friendly. I mean, there's no parameters you have to tweak. So if you're not used to the software, what I recommend is just play around. Get a sample license, get a data set that's fairly simple, that has a lot more observations, that has dimensions. So nice tall skinny data set that has there's a lot of machine learning data sets too available online. You can just play with those. You can Google those and find them. There's some like flower categorization data sets and things like that you can play around with, or you can play around with your own data. And I think that's pretty much what I wanted to cover today. And I know I went through that pretty quickly. The point I wanted to try to make was with, the data set is the important. If you're not creating the model, what are you creating? And the answer is the data set is what you're creating. And if you don't have the data, it's a huge competitive advantage to have that data set. You know, and I know it's very common using a Monte Carlo simulation to interview people to get a distribution. And that is perfectly acceptable in the absence of data. But if you can get the data, you know, through a sensor, I mean, there's a term Internet of Things. You know, if you can put sensors on things, if you can get access to the data set that's relevant to whatever your business model is. For example, the data set I mentioned about Exxon, you know, if you can get access to information on shipping rate, you know, the rate of shipping boats that are going on, something like that. And it takes some creative thought to try to figure out, okay, here's my problem and how do I solve it? Now, if there's no data, obviously there's nothing you can do. I mean, that requires a different approach. And if the data is too expensive, obviously that's a different issue. And you can also see from this, if you didn't already know it, but you can see why data collection for companies like Google and Facebook is so important. Because at that point, you know, the algorithms are, like I said, are a bit of a commodity. But if I want predictive modeling, I need more and more data, and it becomes more and more intrusive. I mean, they're collecting massive amounts of data on you, not because the models they have are really sophisticated, which they are, but because it's a much bigger deal to have a complete data set than it is a fancy model. And there's I forgot the name of the research paper, but I think it's from Microsoft that shows, given the choice between spending money on getting more data or refining the model itself, that it's much better to expand the data set. So like I said, sensors, are you getting information? Like I said, the Fitbit example, I mean, I'll go back to that and I'll finish with this, but you know, if you just talk to me and say, okay, well, how much do you walk per day? And I said, I don't know, about an hour on good, you know, most days, and 2 hours on good days, and 0 hours on days I can't, you know, you say, okay, well, that's probably a per to triangular distribution with, you know, a mean of 1. But let's say you have Fitbit data, and in that Fitbit data, not only can you see which days and hours that I walk, but you can also match that up with, you know, when I have classes, when I'm at work, when the weather's bad, when I'm not feeling well. Okay, now that becomes a significantly more predictive model, because now you can say, okay, it's raining outside. So instead of saying, okay, it's a triangular distribution and, you know, it's going to average 1, I'm going to say, look, it's raining out, so there's almost no chance. My predictive model is going to say there's no chance I'm walking right now. Or it's going to say, okay, it's Monday at 7 p.m. Okay, well, I take my daughter to dance class then. Okay, well, the predictive model would say, yeah, there's no choice. You're going to be walking then. Or if, you know, you record how well I'm feeling. If I wake up this morning and I feel sick, what's the chance I'm walking 2 hours this evening? You know, well, it depends on the data, but probably very low probability. So you can see now it becomes a data collection problem. It's not a distribution fitting problem anymore. It's really a data collection problem. Now, why is it a data collection problem? Because it's a complex relationship. Now, I can simplify that and say, okay, I don't really need that level of detail, and that's fine. You know, a neural network's not a one-stop shopping. It's not going to solve all your problems. It's there for, like I said, categoric or numerical prediction on data that has very complex relationships. If you don't need that, then there's no reason to go through the problem of running it. You know, for example, if you say, like, I don't care how much, you know, when you walk. You know, I'm not trying to predict the day and the hour I'm trying to walk. I'm just getting a general. Then that's fine. Then you don't need to do it. So it's also a problem of what are you trying to model and predict. But it gives you a sense of, okay, once you have this capability, it becomes very, very data hungry. And the neat thing about NeuralTools is it works with Excel. I mean, that's really, really pretty impressive. Now, like I said, you're not going to be doing high-resolution video stuff in Excel. I mean, that's a limitation of Excel, not a limitation of NeuralTools. But for me, you know, I deal with mostly financial data or numeric data. I'm assuming most people on the call, if you're using or thinking about using NeuralTools, it's the same way. So you can see some of the data sets that I showed. I mean, I have millions and millions of observations. I mean, that's more than enough for any data set, financial data set that I have, and that's like a simple handwriting recognition algorithm. So I wanted to end with that I would highly recommend, you know, if you don't have a trial, download it, try the radial basis function network first, because you'll probably get good results. See how accurate it is in your predictions, and, you know, kind of play with the data set, remove features or dimensions, and then rerun it and see what you get. And then I highly recommend attending Michelle's webinar on how to use it. I didn't cover using the software because I wanted to show, okay, because when you open up NeuralTools, it seems very basic, but it's not. There's really sophisticated things going on, but they're just behind the scenes, and it's doing so much work for you. All you really have to do is provide a matrix of data and give it your output to train and test from, and that's it. So sorry, Michelle, I'll end with that, and I don't know if we have any questions, but I'm happy to take any.
I think that was absolutely fantastic. And I do have a couple questions here from a few of our attendees. And before I address those, I do love the fact that you cover the curse of dimensionality in your webinar, because I do think that so many times in the day and age that we're in now, where we collect so much data about so many things, and we think, oh, we have to have all of that data, but really it's a matter of tightening that up. And I love your, you want your data to be tall and skinny. I think that's
Yeah.
important, and you're right. That's what's going to help make that algorithm that much more accurate, is by trimming off the excess fat on it, really. And that's such a great visual for people when they're thinking of the data. We are going to be hosting a webinar, I believe it is June 1st. So we will be doing the neural networks with neural tools and forecasting with stat tools on June 1st at 11 a.m. So this time in a few weeks. And it's going to walk through some of our example files, or what Mr. McGrath referred to as toy data sets. I love that. So yes, we'll use some of the toy data sets that you can then go play with, so that you can start feeling comfortable with the concept of what neural networks can do on a smaller scale. So then you can then apply that to your own. And I want to say thank you, Mr. McGrath, for doing this presentation. It has been super educational and informative, and I believe that this one would be a fantastic candidate for our on-demand webinars as well in the future, so that we can share it with others that were unable to join us today. So I guess that's about it, unless you have anything else, Mr. McGrath.
No, I'd say download the software, and if I remember correctly, the software comes with some really good toy data sets too.
Mm-hmm.
I think the install. So there's really good stuff just on the trial software also.
Absolutely, yes, and that is true. We do have example data files built right into all of our download software. So when you do download our trial software, and in fact, what I'll do is I'm going to pull the presentation screen over to me so I can show you exactly where to find everything. So what you'll do is you'll go to palisade.com, and an easy way to get there is actually to do Decision Tool Suite and download the free trial of Decision Tool Suite, and that will include all of our products, including NeuralTools. So, and even if you went to NeuralTools, the actual software for NeuralTools here, you will also download, that will also be the download of the full Decision Tool Suite. So you can go at it either way, but if you want to learn a little bit more about it, feel free to take a look at our webpage on Neural Tools as well. In addition, we are going to be hosting like I said, the Neural Tools webinar and Stat Tools webinar combined. You can go to the free live webinars here, and if you just scroll down, this one right here, you can go ahead and click on that and register for that one. And that's going to be a little more on the how-to. We figure now we have the theoretical of what happens behind the scenes, and I'll be able to show you in our webinar that we host on the 1st a little bit more of just the technical how-to in Neural Tools itself. So we'll do more of that. So I think this has been fantastic. Again, I want to say thank you, Mr. McGrath, for supporting us all the time. And it's great to have this relationship with you.
No, you're welcome. Yeah, I enjoyed it.
I look forward to hopefully doing another one in the future with you. This was fantastic. And
Thank you.
otherwise, I hope to see you in San Diego maybe for this year's. So thank you so much again, and thank you to everyone else for joining us. We appreciate your time. We know it's not always easy to carve out time on a Friday afternoon, Friday morning, or even Friday evening for those joining us from across the globe, but we appreciate you taking the time out of your day to join us. So I will sign off and say bye for now, and thank you.